So in the section talking about exponential decay, right? Not all things grow exponentially. Some things decay exponentially. This is what that graph looks like. As our x values go to infinity, as they get larger, the y values get smaller and smaller and smaller, but they get smaller at a decreasing rate. So like if we look at the steepness of this line, it's like this, and then it's like this, and then this, and then it's almost flatlined down to nothing, right? So this is modeling caffeine, or coffee, and its the amount of caffeine in your body. It's a temporary stimulant. So the amount that's in your body, in your system, dissipates exponentially. So we can see this happening here, and our author is going to have us run through these numbers by first calculating, first figuring out how much coffee was initially in your system. Well, that's the amount at time 0, right? And that was 180 milligrams. Now, at this point, like, how you drink your coffee would determine how much of this would get in your system. And I don't know if we're assuming like within a 10-minute period you drink the whole cup, but to me it's a bit of a stretch to assume that when you drink your cup, your 180 milligrams are instantly in your bloodstream. The only way I think that you could get that is if you injected it. All right, so regardless of that, we're just going to put our coffee in our system and assume it's there. And then we're going to calculate the relative change. Remember, that's new minus old divided by old. So for that first value, it's 144 is the new value. That's after 1 hour, minus 180 divided by 180. Now, you should get good at looking at these numbers and note, because the 144 is smaller than the 180, we know this is going to be a negative number. When we plug this in Desmos, we get 0.2. I'm going to do one more. So this is negative 20%, since we are to round it to the nearest full percent. I'm going to do the 5 to 6 one. So the 5 to 6 is 47.2 minus 59 divided by 59. Because I've already done this, I know it also calculates out to negative 0.2, or really, really close, right? So it turns out all of these are negative 20%. What does that tell us? It tells us that the decay rate of the decay rate of the caffeine is 20%, meaning it decreases, the amount of caffeine in your body decreases by 20% each hour after you've consumed the full amount. So this helps us know a really important point. A quantity either grows or decays exponentially when the relative change in the quantity is constant. Now, again, we should note, look at all these steps. It's a 1 hour step. If we were given data that looked like this, 2, 4, 6, 8, in our changes, we'd have to be quite careful how we did this new minus old, because this is a step of 2. And exponentially speaking, that's a challenge, because what's happened between the y values is we've multiplied by the growth or decay factor twice. So finding that growth or decay factor requires a little bit of pre-calc and knowledge of logarithms. Okay, so how are we comparing this to exponential growth? Well, see, recall growth looked like this. So as x got really large, the y values increased, whereas decay, if we have the same decay rate as the growth rate, would look like this. So as we get really large values, we're getting really close to 0. Mathematically speaking, the exponential decay graph will never hit 0, which suggests that the caffeine never leaves your system. That's not true. Your body obviously can get it out completely. The only thing I can think of is, I'm sure you've heard about the iron in antiperspirants that supposedly stays in your pores and your armpits and clogs it up and causes cancer and whatever. It's been a while since I've heard about that, but back in the day we talked about that. Okay, so here's a really important question. What's the multiplication factor that you need to multiply by a previous hour's amount to get the next hour's amount? So recall that the decay rate that we found in number 2 is negative 20%. So if we start with 100% of the caffeine in our system, and we know that in 1 hour we lose 20%, the amount that remains is 80%. So the factor we multiply by, which we're going to call B, is 0.8. That's the decimal equivalent of 80%. Let's check it. What's 180 times 0.8? Well, Desmos will tell us it's 144. And so we can do that for all of the values, multiply by 0.8, and we get the next value. All right, so let's turn this into an equation. Okay, we know the B value, the decay factor. We know the initial value, 180. So the equation is simply filling those values in for A and B. Just like the linear equation, we just had to find M and B. Now we just find A and B, where A is the initial value and B is the number we multiply by. We will call it a growth factor if B is a number greater than 1. That's a growth factor. How is it found? It's found by 1 plus the growth rate, which we'll call R. And then if B is between 0 and 1, we call it a decay factor, meaning the values are getting smaller and smaller as X increases. And here B is equal to 1 minus R, where R is the rate. So I'll label R as the growth / decay rate. All right. So you should be able to write any equation you want given this stuff. So let me do, I don't often do this, but this is the first time I think. Let me quick do this did you get it problem. So here we've got this idea that radioactive elements used in medical imaging are good examples of substances that decay exponentially, like iodine 123. It's used in diagnosing thyroid conditions. So this particular isotope decays in such a way that 95% of the initial sample remains. Key word, this is the amount that remains after each 1 hour period. So that means you've been given B, not R. 95% of the stuff does not leave. It doesn't decay at 95%. It decays at a 5% rate. So if we start with 200 milligrams in the system, what's the equation of all of that? You would just do this. Y equals 200 times 0.95 to the X. Okay, let's go ahead and do what we've been asked here now in number 7. Let's recreate that table and the graph in Desmos. So recall that you just type it in, y equals 180 times 0.8 to the X. And we'll click the gear here, we'll click convert to table, and we'll click to the zoom fit so we can get a nice picture of it. And there it is. We don't have all of the values that are in the table, so we could add them in quite easily. 0, 1, 2, 3, 4, so we need 3, 4, 5, and 6. Notice we get a few more decimal places than our table gave us. Quite a bit more, and that explains why maybe if we had calculated the relative change between 6 and 7, we wouldn't have gotten exactly 0.2, negative 0.2, but we would have gotten really, really close. All right, the next thing is how are we going to solve these for various things? How are we going to use the equation to answer various questions? Well, this is the more straightforward one. If we want to know how much caffeine is left in your system after 90 minutes, we just plug that value in for X, but we have to be careful. Remember, X is labeled in hours. So how many hours is 90 minutes? Well, let's go back to what? Unit 2.2 or Unit 1 where we did a conversion factor. We want to convert this into hours. So we know 1 hour is equal to 60 minutes. So the minutes will cancel. Let's see, these zeros go away, and we get 9/6 hours. That's also 3 halves, doesn't matter. Desmos will take it either way. We tend to like things simplified. Alex will ask for that as well. You could also write this as 1.5 hours. All 3 of those representations are the same. Since this is the X value, we're just going to plug it in here for X. So we're going to do y equals 180 times 0.8 to the, let's do 1.5. It's the easiest to type in. So we'll put, well, I've got the table here. Why not just type it right here? 1.5, there it is, 128.797525. But if you didn't use that table, you would write it like this, and you get the same answer. So that's approximately 128. If we do 2 decimal places, this would be 80 milligrams would be our correct answer. Because that's 797, the 9 around, the 7 up. All right, then we're to estimate the amount of time needed for the caffeine to drop to 40 milligrams. Okay, well, if we look at our graph, I'm going to zoom in a bit. So here's 100, and we got what? 1, 2, 3, 4, 5 tick marks. So if I divide 100 by 5, each one of these is 20. So 40 is right here. And we just have to find, where does this line cross 40? It's right there-ish, right? 50, yeah, 40 is like right here. It looks like, what, 6.6? In other words, it's between 6 and 7. You can also see that over here in the table. Why don't we just find it exactly, right? We've got this awesome Desmos calculator. That 40 milligrams is a Y value. Type in Y equals 40, and let's click where these graphs cross. Oops, we can't do it when it's a table, so we just have to retype the equation. Y equals 180 times 0.8x, and then we can click the intersection point, and we get that the x value is 6.74 hours. That's the best approximation of that value. I'm going to expect you to be able to do this on the Unit 2 Review B worksheet. And I say show your work. So this is how you show your work. You would draw in the graph the exponential function, you draw the y equals 40, and then you'd show that they intersected here, and that is about the 6.74 hours. That would be work shown. Because what you're really doing is you're trying to take this equation, y equals 180 times 0.8x, and you're replacing the y with 40. So you're looking to solve this. Well, unless you've taken pre-calculus, or you remember from Algebra 2, if you got that far back in high school, you would divide these things, and what you get 4/18 equals 0.8 to the x, and it's like, how do I get rid of this? Now it's a logarithm. I'll just type this in here, and if you all know this, that's awesome. You would take log 0.8 of 4/18, and that's equal to x. That's how you solve it, but I would not expect you to know how to do this. Logarithms are totally outside the scope of this class. What we're going to do instead is just use this graphical method to solve.